Gravity is a fundamental force of nature. It is a force of attraction. This force pulls objects towards each other. We experience gravity every day. Gravity makes things fall to the ground. It keeps us on Earth. Gravity governs the motion of planets. It holds stars together in galaxies. Without gravity, the universe would be a very different place. Gravity is always working. It is an invisible force, but its effects are all around us. Understanding gravity helps us make sense of the world. Sir Isaac Newton was a brilliant scientist, mathematician, and astronomer. His contributions to science are immeasurable and have shaped the way we understand the world today. He made groundbreaking discoveries about gravity, optics, and calculus. His work laid the foundation for classical mechanics. One day he was sitting under an apple tree contemplating the mysteries of the universe. An apple fell from the tree, a seemingly mundane event that would lead to a monumental breakthrough. This simple event sparked a revolution in scientific thought. Newton began to ponder why the apple fell straight down and not sideways or upwards. Historian Newton realized that the same force that pulled the apple down also governed the motion of the moon and other celestial bodies. This was a profound insight. He called this force gravity, a term that would become fundamental in the field of physics. Newton's insights changed our understanding of the universe. His theories explain not just the falling apple, but also the orbits of planets and the behavior of tides. Newton formulated the law of universal gravitation, which states that every mass attracts every other mass in the universe with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law explains how gravity works both on Earth and in the vast expanse of space, providing a unified description of gravitational force. It is one of the most important laws in physics, influencing countless scientific advancements and our understanding of the natural world. Newton's legacy continues to inspire scientists and thinkers to this day. Newton's law of universal gravitation is a simple but powerful idea. It states that every object in the universe attracts every other object. This attraction is gravity. Scientist. The strength of gravity depends on two things. The first is mass. Objects with more mass have a stronger gravitational pull. The second factor is distance. The closer objects are, the stronger the gravitational attraction between them. Newton's law can be summarized with a simple equation. It allows us to calculate the force of gravity between any two objects. We experience the force of gravity all the time. On Earth, gravity pulls us towards the center of the planet. This pull is what gives us weight. Student weight is the force of gravity acting on an object's mass. The more massive an object, the heavier it feels on Earth. Gravity keeps us grounded. It prevents us from floating off into space. It also influences the shape and motion of our planet. Section 5. Beyond the apple gravity's impact on our world. Modern physicist. Gravity's influence extends far beyond falling apples. It shapes our world in countless ways. Tides are one example. The moon's gravity pulls on Earth's oceans. This creates bulges of water on opposite sides of the planet. Modern physicist. These bulges are high tides. Gravity also plays a crucial role in the water cycle. It pulls precipitation down from the clouds. It drives the flow of rivers and streams. Section 6. The tides, a gravitational dance. Scientist, tides are a fascinating phenomenon. They demonstrate the power of gravity over long distances. The moon's gravity is the primary cause of tides. The sun also plays a role. The sun's gravity is much stronger than the moon's. However, the moon is much closer to Earth. Scientists, this proximity means that the moon's gravitational pull has a greater influence on the tides. The alignment of the sun and moon can create spring tides or neap tides. Section 7. Weightlessness escaping gravity's grip. International student. Astronauts in space experience weightlessness. This means they feel like they are floating. Weightlessness is not the absence of gravity. It is the feeling of free fall. International student. Astronauts in orbit are constantly falling towards Earth. However, they are also moving forward at a very high speed. This forward motion prevents them from crashing into the planet. International student. The result is a state of perpetual freefall or weightlessness. Section 8. Black holes. Gravity's ultimate triumph. Black holes are some of the most extreme objects in the universe. These enigmatic entities have fascinated scientists and the general public alike for decades. Their mysterious nature and the extreme conditions they create make them a subject of endless curiosity and study. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull warps the fabric of space-time itself, bending light and distorting our view of the cosmos.
Black holes form when massive stars collapse at the end of their lives. This dramatic process often follows a spectacular supernova explosion where the outer layers of the star are ejected into space. The star's core collapses under its own gravity, leading to a catastrophic implosion. This collapse is so intense that it compresses the core to an incredibly small size. This creates a point of infinite density called a singularity. At the singularity, the laws of physics as we know them break down and our understanding of the universe reaches its limits. The singularity is surrounded by an event horizon. This boundary marks the edge of the black hole and is the point beyond which nothing can return. The event horizon is the point of no return. Once an object crosses this boundary, it is inexorably drawn towards the singularity, unable to escape the black hole's immense gravitational pull. Once something crosses the event horizon, it cannot escape the black hole's gravitational pull. This includes everything from particles of light to entire stars. The journey beyond the event horizon is a one-way trip into the unknown, where the mysteries of the universe are locked away, hidden from our view.
Section 9. Gravity's role in the cosmos, shaping the universe. Gravity is the architect of the universe. It brings matter together. It forms stars, planets, and galaxies.
Gravity governs the motion of celestial objects. It determines the structure of the cosmos. Gravity is also responsible for the expansion of the universe. The Big Bang theory suggests that the universe began as a hot, dense state. Gravity caused the universe to expand and cool. Over billions of years, this expansion led to the formation of the structures we see today.
Section 10. Unifying forces, the quest to understand gravity. Gravity has always been a mysterious and fascinating force, pulling us towards the Earth and keeping the planets in their orbits. But what exactly is gravity, and how does it fit into the broader picture of the universe? Gravity is one of the 4 fundamental forces of nature. These forces govern the interactions of matter and energy in the universe, shaping everything from the smallest particles to the largest galaxies. The other 3 are the electromagnetic force, which is responsible for electricity and magnetism, the weak nuclear force, which plays a key role in radioactive decay and nuclear reactions, and the strong nuclear force, which holds the nuclei of atoms together, binding protons and neutrons with incredible strength.
Physicists have been trying to unify these forces into a single theory for decades. This quest, often referred to as the search for a theory of everything, aims to find a single framework that can explain all the fundamental forces and particles in the universe. This theory would explain all the forces of nature as different aspects of one underlying force. Such a unification would revolutionize our understanding of the universe, providing a deeper insight into the fundamental workings of nature. Einstein's theory of general relativity describes gravity as a curvature of space-time. According to this theory, massive objects like stars and planets warp the fabric of space-time, creating the effect we perceive as gravity. However, general relativity is incompatible with quantum mechanics, which describes the behavior of matter at the atomic and subatomic levels. Quantum mechanics operates on principles that seem to contradict the smooth, continuous nature of space-time described by general relativity. This incompatibility has led to one of the biggest challenges in modern physics, finding a way to reconcile these 2 foundational theories into a single, coherent framework. One of the leading candidates for this unification is string theory, which proposes that all particles are actually tiny, vibrating strings. String theory suggests that these strings vibrate at different frequencies, giving rise to the various particles and forces we observe. It also introduces the concept of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. Experiments in particle accelerators and observations of cosmic phenomena continue to provide clues, but the quest to fully understand gravity and unify it with the other forces remains one of the most profound and exciting challenges in science.
Section 11. Conclusion. Gravity's enduring enigma. Gravity is a fundamental force that shapes our universe. From falling apples to orbiting planets, gravity is everywhere. Newton's law of universal gravitation provides a basic understanding of how gravity works.
Einstein's theory of general relativity offers a more complete description. Despite centuries of study, gravity remains one of the most mysterious forces in nature. Unifying gravity with the other fundamental forces is one of the biggest challenges in modern physics. Solving this challenge could unlock new secrets of the universe.